Welcome to the video on conjugated pi systems and ultraviolet visible spectroscopy, or UV Vis. So there's a couple different types of dienes. Accumulated, which means they're right next to each other. Conjugated, which is what this chapter is about, where we have double, single, double, single, double. And isolated, where they're just kind of off on their own and independent. If we look at the p orbitals of the pi bonds in these three types of dienes, you can see that this situation with the culminated are very unstable. We have these perpendicular pi bonds right next to each other. Conjugated are actually very stable, and we can have delocalization of the electrons around the entire system. And isolated are just two independent alkenes, and there's no delocalization possible. This chapter focuses on conjugated systems and the special properties and reactivity that they have. Heteroatoms can also be involved in a conjugated system. For example, we have an oxygen here and a nitrogen here. Those are still considered conjugated systems, so it doesn't have to just be carbon-carbon double bonds. It can also be carbon-oxygen and carbon-nitrogen. Part of the reason why conjugated dienes are so special is the bond length. So if we have a situation where we have a double, single, double bond here, that single bond that is sandwiched between the two alkenes has a bond length which is much shorter than that of the typical single carbon-carbon bond. And that is because of delocalization, and it is because of the fact that that single bond is an sp2 overlap versus the sp3 overlap of a typical alkane. And if you think about that delocalization, we also use the term resonance to describe that phenomenon. From the acid-base chapter, the more S character we have, the shorter the orbitals and the shorter the sigma bonds will be. A p orbital has 0 S character, and sp3 is 25% S character, and sp2 is 33% S character, and sp is 50% S character. And of course, an s orbital is 100% S character. So the sp2 orbital overlap is going to be shorter and stronger than an sp3 orbital overlap. So evidence that helps determine the fact that these conjugated dienes are more stable comes from heats of hydrogenation. The heats of hydrogenation is the energy given off when we add hydrogen across a double bond. An isolated alkene here, taken twice, it is 254 kilojoules of energy given off when that becomes the alkane. Whereas if we have the conjugated diene here, again, that's two alkenes just like this, so they're equivalent, but this one is conjugated, we actually have only 239 kilojoules per mole given off. So there's a 15 kilojoule per mole stabilization energy when the bonds are conjugated. So for class, why don't you see if you can determine which one of these compounds is the most stable based on conjugation. So generally, that sigma bond that's in between the two alkenes has free rotation, and when that happens, we can adopt the S cis, where the two double bonds go in the same direction, or the S trans, where they go in opposite directions. We talked about this when we talked about Diels-Alder. The S trans is actually more stable because it has less steric hindrance. With conjugated dienes, we can look at that stability and describe that stability a couple different ways. We can use our pushing electrons, resonance, delocalization approach to describing that stability, or we can use molecular orbital theory. So the next couple slides, I'll talk about molecular orbital theory and conjugated dienes. Remember, when two atomic orbitals overlap, they form two new molecular orbitals. So if we have a 2p electron here and a 2p electron here, when they form that pi bond, we have two new molecular orbitals formed. One is going to be a bonding orbital, and one is going to be an anti-bonding orbital. With the bonding orbitals, the molecular orbitals are more stable than the original atomic orbitals. Anti-bonding are less stable than the atomic orbitals. So for this situation right here with ethylene, we have one bonding molecular orbital that is filled with two electrons, and one anti-bonding molecular orbital that is empty. And if we were going to talk now about butadiene, which is this molecule, here's our 4 atomic p orbital electrons. So if 4 atomic p orbitals come together, we have 4 new molecular orbitals. 2 are going to be bonding and 2 are going to be anti-bonding. And so in the situation with the lowest energy, we have all positive at the top, all negative at the bottom. So this is in phase and constructive. in terms of the arrangement of our orbitals. If we go up one level, we end up with one node, which means we have positives here interrupted and we have negative here. And so we have one node. And if we keep moving up in energy, we increase the number of nodes. We have two nodes here. And in our highest energy antibonding molecular orbital, we have three nodes. The 4 electrons in butadiene are going to occupy the lowest molecular orbital. So these are the 2 bonding orbitals, and we have our 2 electrons in the lowest with 0 nodes and in the second lowest with 1 node. In the lowest energy case, we have double bond character because the C2 and the C3 constructively overlap. In the next level of energy up, we do not have double bond character because we have these 2 things are out of phase and they do not constructively overlap. Because in our 2 bonding molecular orbitals, only one shows double bond character, that means it's not a true double bond, but it is a partial double bond. So molecular orbital theory offers an alternate explanation as to why that CC bond is shorter and stronger than a typical sigma bond. And that is because in the lowest energy state of the molecular orbital, this is constructive and that does have a partial double bond character. We can go further into hexatriene, where we bring 6 p orbitals together with 6 electrons, 6 molecular orbitals, 3 of which are bonding and 3 of which are antibonding. And again, we have 0 nodes, and then we increase the nodes as we go up, and the top highest energy antibonding orbital has 5 nodes. And if you wanted to draw 1, 3, 5 hexatriene, that would look like this. Reactions that molecules undergo can often be explained by studying their frontier orbitals. And light can be used to actually excite the electron from the HOMO, highest occupied molecular orbital, to the LUMO, lowest unoccupied molecular orbital. We have hexatriene. Here is the highest occupied molecular orbital because we have 2 electrons here. And this right here is considered our LUMO because it's the lowest unoccupied molecular orbital. Now, if we use UV or visible light to excite an electron from the HOMO to the LUMO, that becomes our HOMO and that becomes our LUMO. When we promoted an electron like that, that is called the excited state. UV Vis spectroscopy is often used to determine whether systems have conjugation or not. Compounds with conjugated pi systems absorb UV light and or visible light. And so when we have our ground state and we put energy in, or UV light, that is going to excite one electron, and the light that we put in is converted to potential energy in our molecular orbital diagram and in our molecule. So typically when we promote an electron from the HOMO to the LUMO, we call this a pi to pi star transition. So we're talking about pi bond electrons, and pi is the bonding molecular orbital and pi star is the anti-bonding molecular orbital. And so this would be pi and this would be pi star. And so when we promote that electron from pi to pi star, the energy is very typically in the UV and visible region of the electromagnetic spectrum. Ultraviolet visible spectroscopy gives us information about a molecule's conjugation. So the amount of light that's absorbed by a sample is a function of the wavelength, also called absorbance, and that ultimately tells us about the conjugation. If we were to look at butadiene here, we get a UV Vis spectrum shown below right here. So on the x-axis is wavelength, and on the y-axis is absorbance. And we get a trace as we walk along the different wavelengths. This has a lambda max, or the maximum absorbance of the spectrum is 217 nanometers. And remember, absorbance is related to incident light. So the more conjugation a system has, there's a smaller distance between the pi and the pi star. So as we have increased conjugation, our molecular orbitals are packed tighter and there's less energy difference between them. The smaller the energy gap, the greater the lambda max. So a small lambda max means we have a slightly conjugated system. A huge lambda max is going to indicate that we have a lot of conjugation. And if we look at the differences in energy level, if we have 4 molecular orbitals, the distance between pi and pi star is shown here, meaning that this one requires more energy to excite that electron. And if we have 6 molecular orbitals, that distance decreases, which requires less energy to excite that electron. And if we have 8, it decreases even more, requiring even less energy. And remember, that's a higher lambda max value. So the more conjugated a system is, the more stable it is, and the less energy we need to put in to promote an electron from the HOMO to the LUMO. And if you wanted to quantitate this or use values, 217 nanometers versus 258 nanometers versus 290 nanometers. Even though the lambda max value increases, the energy actually decreases. A highly conjugated compound can absorb in the visible region of the spectrum. For example, lycopene, the red in tomatoes, and beta carotene, the orange in carrots, those are visible. And look at the conjugation that exists in this molecule. So those values are going to be very high. And the same with beta carotene. That conjugation is incredible, and that is going to mean that we don't need ultraviolet light to make this transition from the HOMO to the LUMO. We actually can use visible light, which is even less energy and a higher wavelength. Recall that ultraviolet light is right next to visible light at the purple end of the spectrum. As the energy increases from the left hand to the right hand side of this figure, wavelength decreases. So as energy increases, wavelength decreases. They are inversely related. Here is a figure that helps us comprehend that difference in wavelength. For example, radio waves to gamma rays goes from the size of buildings to the size of subatomic particles. Bottom line, visible light has less energy and a higher wavelength than ultraviolet light. So remember the color wheel, right? So if we observe a color, it's actually the opposite color that's being absorbed, right? Because what's reflected is what we see. And so the color observed by your eyes will be the opposite of what is required to cause that pi to pi star excitation. Okay, so I'd like you to think about which one of these dienes will have the highest heat of hydrogenation. So remember, heat of hydrogenation is the energy given off when it goes from an alkene all the way to an alkane. How many electrons does the HOMO of 1,3-pentadiene have in its excited state? And which one of the following represents the highest energy pi anti-bonding molecular orbital of 1,3-butadiene? And finally, which molecule below do you think will have the shortest distance between the HOMO and the LUMO? Okay, there you have it. Conjugated pi systems and UV Vis spectroscopy.